Hello and welcome back to my channel. Students, as you all know, we are doing organic chemistry through problems. So what I try to do is to create problems which includes fundamentals of organic chemistry. Through these problems, I try to make you learn the concepts of organic chemistry. And in this process, I have already covered general organic chemistry, and we have now started a new topic, stereoisomerism. So now let us try to see what is there for us in question number 28 based on stereoisomerism. So students, as you all now can see that I have mentioned some 6 compounds with their 3-dimensional diagram on your screen. Out of these 6 compounds whose structural formula, whose 3-dimensional formula is given on your screen, you have to tell how many of these are chiral in nature. Now, in the previous video, I have already told you what is the meaning of chiral carbon or a chiral center. Saying a chiral carbon or a chiral center is different from saying a chiral compound. I will give you a few examples before I have started predicting the chiral compound behavior. So if you try to see, first of all, that there are pictorial representation on your screen. What is the meaning of these pictorial diagram? First of all, you understand the 3-dimensional figure you see on your screen is called as wedge dash or flying wedge projection. Now, in the wedge dash formula, you have a carbon at the center, and with this carbon you have 4 bonds. These 4 bonds are tetrahedral in dimension in 3-dimensional figure. How the tetrahedron can be drawn, as you can see, these 2 yellow lines are 2 bonds which are on the plane of paper. The paper I mentioned, basically you can treat that as my screen. So the yellow lines are the bonds on the screen, on the plane of a screen. The wedge, which I have mentioned as wedge, is coming out of the plane of paper, and the dash which I have represented is going inside the plane of paper. So a tetrahedral carbon can be shown in 3-dimensional formula as I have mentioned, flying wedge projection. Again, the 2 solid lines, yellow lines, are on the plane of paper. The dash line is going inside the plane of paper. The wedge is coming outside the plane of paper, and that is how you show a tetrahedral 3-dimensional figure, and is called as flying wedge or wedge dash projection. Now, based on this formula and the meaning of formula, let us try to see what is the meaning of chirality. Student, you should understand, if I say a compound is chiral in nature, then I specifically tell that if you make mirror image of the 3-dimensional figure of that compound, the compound itself and its mirror image, both will be non-superimposable on each other. So chirality means non-superimposable on its mirror image. So again, if any species, you have to predict whether the whole compound, whole species is chiral or not, you have to first take its three-dimensional diagram. Then you take its mirror image. If both are not fitting ditto on each other, both are non-superimposable, then in that case you say that the two are different compounds, the two are enantiomers, or the two are not the same. That is what is the meaning of chirality, non-superimposable on mirror image. Now let us take example A. So in the A compound I have taken in my question, as you can see, I have this as a compound. The three-dimensional figure is in front of you. I have taken a mirror and I have drawn the mirror image. As you draw the mirror image of this compound A, you find that if you try to superimpose the two on each other, so let us call this as 1 and the image as 2. Now once I say that you try to superimpose, what I mean is all the groups must be ditto placed on each other. If it is not happening, not possible, then the two are called as non-superimposable. So if you try to do so, I have tried in a manner so that I can convince you that this figure is not going to match ditto on its mirror image. For that to happen, let us try to see how I have done. You understand, I have turned this, you take this compound and you just rotate it 180 degree like this. So you rotate it 180 degree. So as you rotate it 180 degree, keeping this bond intact, so keeping CH3 intact, you rotate the Cl 180 degree. Once you do that, this Cl will come here. This fluorine, which was earlier going inside, as you rotate 180 degree, it will now come outside. And this Br, which was earlier coming outside, now will go inside like this. Now if you try, and both are same thing because you have not done anything. I mean, for an example, this is my pad, you can see, if I turn it like this or that, it's going to remain the same. Turning a compound, rotating a compound does not change the compound. So what I did, by turning it 180 degree, it remains the same. I just wanted to let you know that this figure, if you try to superimpose with this, so what most you can do? The most you can do is you will try to superimpose the methyl with methyl, the Cl with Cl, and once you take this and try to superimpose this on this, the methyl is going to be sitting on methyl, the Cl is going to be sitting on Cl, but in that course the Br will sit on fluorine because both are going inside, and fluorine will sit on Br because both are coming outside. So in that sense, although the two sat on each other ditto, the other two were missing out. They were not sitting ditto on each other, and that is why we are saying that the two are non-superimposable mirror images. So these two are not same compound, they are not identical, but they are different compounds and are mirror images or isomers of each other. And these isomers are specifically called as optical isomers or enantiomers, and the enantiomers or the optical isomers comes under the category of stereoisomers. So the two mirror images, if these are non-superimposable on each other, we call them separate, and these separate are isomers of each other, and the name of isomerism is called as optical isomerism or enantiomerism, and these two are optical isomers of each other, enantiomers of each other. So this is very important, and the moment you find this property of non-superimposability, the two compounds which are mirror images, non-superimposable mirror images, are chiral in itself. I mean, the compound 1 and the compound 2 both are called chiral compounds and are mirror images of non-superimposable mirror images of each other. So now I will again take up A and I have, as I have written, I have tried to explain, since 1 and 2 are non-superimposable, therefore these are not same but are isomers of each other, called as enantiomers or optical isomers, and these are stereoisomers. Okay, so that is very important to realize. Chirality is related with non-superimposability on its mirror image. It tells that the compound is not symmetric. The compound as a whole is asymmetric. The compound as a whole is chiral. And if the two mirror images are superimposable, they match on each other ditto, these are called as identical, and the compound will be called as achiral or symmetric. So that is very important to understand. Now coming on to the question, the part B, the compound number B in my question. As you can now see that again there is a carbon with the 4 bonds, as I have mentioned. In order to check the chirality, as I have already told you, you should take the mirror image of this compound, and as you take the mirror image, you try to superimpose the two on each other. And as I have tried to do so, you understand, first of all, what I did, I just rotated this by 180 degree. As you understand, as I rotated this 180 degree, the methyl will go here, the iodine which was earlier going inside will come outside, and the hydrogen coming outside now will be inside. Now what I did, I kept methyl in the same position. I just rotated the 3 this way. As I rotated the 3 this way by 120 degree, you understand, this iodine will come here, this iodine will go there, and this hydrogen will come here, and you will get this diagram. Okay, so I took the compound, held the methyl same position and rotated it 120 degree like this. It will not change the compound, and from here I got this figure. And once you see this figure, this is exactly superimposable on 2. Why? Because if you try to superimpose, the iodine matches on iodine, this iodine matches on this iodine, this hydrogen matches on this hydrogen, and this methyl matches on this methyl. So in the last 2 examples which I took, the example number A, we saw that the compound and its mirror image were non-superimposable, and therefore the two were different and were called as enantiomers of each other, and both were chiral in nature. This case, as I took the mirror image, we saw that both are going to superimpose on each other identical, and therefore these two are not different but identical, and therefore this compound is achiral. Once I say achiral, it means that it is not chiral. Okay, the chirality is a very important property, you understand. Once we detect that a compound is chiral by doing this procedure, by drawing its mirror image, the mirror image of its 3-dimensional figure, trying to see the superimposability. If both are non-superimposable, we say that the compounds, the two are different and are chiral in nature. Chirality has to do with the optical behavior. That I will take up in some later videos. where I will explain you that once a plane polarized light is passed through a chiral compound, then it turns the plane polarized light either clockwise or anti-clockwise. So that is a trademark property of a chiral compound, that it has a behavior towards a plane polarized light. It turns the plane polarized light either clockwise or anti-clockwise. However, if the compound is achiral, then if you pass the plane polarized light across it, through it, then it will not turn the plane polarized light either clockwise or anti-clockwise. That is a very important and major distinction between chiral and achiral compounds. Now, coming on to the case number C. So now again, this is, as you can see, the case number C. A carbon is there and the 4 bonds as I have drawn in the flying wedge projection. You can see, to see the chirality I have to draw the mirror image, and again what I did, this one I turned it 180 degree. As I rotated it 180 degree, this hydrogen comes here, the tritium, it goes outside now, the chlorine, it goes inside now. Now you understand, if I try to superimpose these two, the deuterium matches on deuterium, the hydrogen matches on hydrogen, but this Cl will lie on tritium and the tritium will lie on Cl. It shows that these two are non-superimposable, therefore these two are different compounds, these two are stereoisomers of each other, these two are optical isomers of each other, these two are enantiomers of each other, and these two will show optical behavior. If you take any of one or two and pass the plane polarized light, it will rotate it either clockwise or anti-clockwise. That means these two are chiral in nature. Now from the 3 examples, if I revisit my question before I have proceeded, the 3 examples as you see example number A, it was chiral. I proved it by making the mirror image. Example number B, it was achiral as the mirror image and it superimposed. The C, the chiral. Now if you try to see the results of superimposability and the chirality and the groups which are attached with the carbon, you notice a very important feature. The A and C, as we have called them chiral, have got special property. What that special property is? The carbon, you understand, all the 4 groups are different. You understand? Here also, all the 4 groups are different and isotopes are taken as different groups. So you understand, all the 4 groups if different, and only one chiral carbon is there. You understand? Both A and C had one chiral carbon, just one chiral carbon each. On the other hand, the B, which got superimposed on its mirror image or is achiral, is not having any chiral carbon. No chiral carbon it has, because you understand these 2 groups are same, and I have already told you, to be a chiral carbon, all the 4 groups attached with that carbon must be differently substituted. So from here now we can have a very important observation, as I have written here, as you a very important lesson to be taken. If a compound has just, this is important, has just one chiral carbon, this is very important, then it will always be chiral as a whole. So this final statement, after taking the 3 examples into consideration is very important. If you see a compound, the 3-dimensional diagram, that it has got just a single chiral carbon, then for sure if you are going to make its mirror image, both are going to be non-superimposable and the compounds will be chiral in nature. However, if it does not has any chiral carbon, then there is a suspicion. Then I will take up the cases. For an example, the previous case I took, the case number B, it did not has any chiral carbon, so you understand it was superimposable on its mirror image and was achiral. Okay, and it is subjected to more discussion that I will take up in my future videos. Now coming on to next, the example number D. In the example number D, you understand, again you don't have to do much effort provided you have learned the lesson importantly from the previous cases. If you see this carbon, this is a chiral carbon. Why? Because the 4 groups are different: methyl, chlorine, bromine, and this group you understand, CH2Cl. The 4 groups are different, so there is just one chiral carbon. Why? Because the other carbon you understand has got 2 same groups, therefore this is not chiral. So again you understand, you have a compound in front of you that is having just one chiral carbon, so you don't have to worry about this. Although I have made the mirror image, and if you try to superimpose the 2 on each other, you will not be successful because both are chiral in nature. Both are enantiomers of each other, so the 2 mirror images are not superimposable on each other, and it has happened because the compound had just one chiral carbon. Now what happens if you have more than one chiral? So before we leave this page, let us read out. Just one chiral carbon, therefore surely chiral compound. Now coming on to the example number E. Once you now see the example number E, you understand, if you take these 2 carbons and try to understand whether the chiral carbon, before chirality I am just looking for the chiral carbons. You see, if you see the top carbon, the 2 groups are same, both are hydrogen, so the top carbon cannot be chiral, so it's not chiral. If you see the bottom carbon, again it has 2 same groups, so again this is not going to be a chiral. So you understand, it is similar to the case number B, where the compound is not having any chiral carbon. So if you try to draw the mirror image, also I have drawn the mirror image, and by drawing the mirror image I have tried to let you know that the 2 are not superimposable. How? You just take this and you rotate the whole molecule like this. As you rotate it by 60 degree, you understand, this methyl, as you have rotated this methyl from here, it will go here. So you understand, earlier it was going like this, now it will go like this, so methyl will come here. This hydrogen will come here, and this hydrogen moves there. So as you understand, 60 degree as you have moved, this hydrogen has moved. Earlier it was coming outside, now it will be on the plane of paper, and earlier this was on the plane of paper, now it will come outside like this. So 60 degree you have turned like this, and the same will happen with the below also. This Cl will go inside 60 degrees, so it will go inside. This hydrogen will come like this 60 degree, and this Cl will come outside 60 degree, because whole compound you are rotating by 60 degree, so it will come on the plane of paper. So if you now try to superimpose these 2, you see these 2 are same. These 2 are same. If you try to take this below one to match on the above one, the mirror image, both are ditto same. That is why I am saying this is not a chiral compound, is achiral. So take a lesson from the examples B and E. If the compound is not having any chiral carbon, again you listen, if the compound is not having any chiral carbon, then it will be achiral in nature provided all the atoms which are involved, are carbon and hydrogen. And there are some cases, for an example we will see in future, that because of some ring, because of some double bonds, the chirality may come. But most of the cases you will find that if the compound is lacking the chiral carbon, it will be achiral in nature. In almost many cases. A few exceptional cases are there, I will take up in my videos, where chiral carbons won't be present, then also it will be chiral in nature. Next, if you come to the example number F, in the example number F, as you can see, you have two chiral carbons in your on your screen. The top carbon, you understand, the four groups are different as you see, and the below also the four groups are different as you can see. If you draw the mirror images, the two are not superimposable on each other, therefore both are chiral in nature. Now here I want to make a strong comment that if you have more than one chiral carbon, look, if the compound has just one chiral carbon, it will definitely be chiral in nature. If it has no chiral carbons, most of the cases it will be achiral, it will not be chiral. A few cases are there, I will take up afterwards. But if you have more than one chiral carbon, then in some cases chirality will be there, and in some cases the chirality will not be there. You should understand here, although you got the two images are non superimposable on each other, you don't remain assured that if more than one chiral carbon is there, you will definitely going to get the chirality. No, it may happen, it may not happen. For an example, this example you have seen, you may try whatever you want, the two are not going to superimpose on each other. So both are enantiomers of each other, both are optical isomers of each other, and both are independently chiral in nature. However, I have given one more example. As you can see in your figure, I have now taken a different, out of my question, it is not included in question, just for the sake of information. You understand the two carbons up and down, both are differently substituted, so both are chiral. Now you take the mirror image, I have taken the mirror image, and I have shown that although it had more than one chiral carbon, but the compound is not chiral because both are superimposable on each other. How? What you do, you turn this like this. What do? You turn it like this, upside down. So if you do it like this, if you do it upside down like this, so as you do this, you understand, you will get this figure. And as now you have got this figure, you rotate the top three groups by 60 degree like this, and the below also 60 degree like this. So here also 60 degree, there also 60 degree. You will get this figure. And once you see these two figures on your screen, both are ditto matching on each other. Both are ditto matching on each other. So what does it reveal? It reveals that although it had more than one chiral carbon, that is two chiral carbon, but still the two mirror images were superimposable on each other. So the presence of more than one chiral carbon does not ensures it does not guarantees the chirality of the compound. However, if it has got one chiral carbon, it ensures the chirality. However, if there are no chiral carbon, most of the cases you will see the chirality is not there. However, there may be cases I will take up in future that although the chiral carbons may not be there, but still the compound is chiral. So these are very important and strong statements as I have told you, and most of them I have covered using my examples. So I hope you all must have understood the basic and the fundamental details about the chirality. So again, the chirality is a feature where you have to make a mirror image. then the two, if are not superimposable on each other, both are different compounds, both are chiral in nature, and both are stereoisomers of each other, called as enantiomers or optical isomers. However, I have given a few tricks also to see whether the chirality may be there or not. The very important one is if you have just one chiral carbon in the compound will be chiral in nature. There will be chirality. However, if you have more than one chiral carbons, you may or you may not have the chirality. However, in the absence of chiral carbon, most of the cases you will see the compound is achiral, but there are certain other features also which we will see in our future videos that may bring the chirality. And if you draw the two mirror images, both are non-superimposable on each other, although there was no chiral carbon in the compound. So I will take up those in the future videos. Till then, take care of yourself, keep a good check on your health and happiness. Thank you very much.